Hello guys, in this video I will solve questions of complex analysis from wbset 2024. So the first question is, let I equals to z to the power 4 e to the power 1 by z dz where c is given by mod z equals to 4. Then we have to find the value of I. So mod z equals to 4 is a circle centered at origin and radius 4 unit. Then the solution is z to the power 4 is analytic everywhere, we know that, and e to the power 1 by z has essential singularity at z equals to 0. Then z to the power 4 e to the power 1 by z has essential singularity at z equals to 0. So what we will do, we will find the series expansion of e to the power 1 by z to find the residue. Okay, so z to the power 4 as it is, and the series of e to the power 1 by z is 1 plus 1 by z plus 1 by 2 factorial z square and so on. So we have to find the coefficient of 1 by z, and coefficient of 1 by z will be obtained when z to the power 4 will be multiplied by 1 by z to the power 5, and then the coefficient of 1 by z equals to 1 by 5 factorial, which is 1 by 120. Therefore, integration I equals to 2 pi I sum of residues at z equals to z naught, where z naught is the point of singularity. Then 2 pi I into coefficient of 1 by z is the residue, we know that. Then 2 pi I into 1 by 120 equals to pi I by 60. Then answer is option D. Option D is correct. Pi I by 60. Next question is, if 2x minus x square plus ay square is a harmonic function, then the value of a is. So we have to find the value of a. The only condition given is it is a harmonic function. Then we have to use the Laplace equation, because a harmonic function will satisfy Laplace equation. Let u equals to 2x minus x square plus ay square. Then ux equals to 2 minus 2x, uxx equals to minus 2x. Ux is nothing but the partial derivative of u with respect to x. Uy equals to 2ay, uyy equals to 2a. Then the Laplace equation is uxx plus uyy equals to 0. That implies minus 2 plus 2a equals to 0. That implies 2a equals to 2. That implies a equals to 1. Hence, option A is correct. Now we have to find the false statement. Which of the following is false? Option A is an entire function maps bonded set to bonded set. A non-constant entire function is unbounded. Option C is a non-constant entire function maps unbounded set to unbounded set. Option D, there exists an entire function having infinity as its regular point. So first of all, we will solve option number B. What is option number B? A non-constant entire function is unbounded. Then this is nothing but the Liouville's theorem. Then it is true, right? It is Liouville's theorem. Then we will solve option D. What is option D? There exists an entire function having infinity as its regular point. So we have to see whether there is any function or not. We know that constant functions are entire. Let fz equals to k, where k is a constant. Then fz is a constant function and f of infinity is also k. Hence infinity is not a point of singularity. Therefore infinity is a regular point of fz. Then option D is also true. Next, option A. What is option A? An entire function maps bonded set to bonded set. So for option A, let f be an entire function. Then f is analytic on any bonded set, as entire means analytic on the entire complex plane. Hence f of D equals to bonded set, where D is a bonded set. Because if D is any bonded subset of the complex plane C, then inside D, F is analytic, then F will map bonded set to bonded set. Now, option C, a non-constant entire function maps unbounded set to unbounded set. So let us see whether it is true or not. Let fz equals to e to the power z and gamma equals to z belongs to C such that x less than 0. Then mod fz equals to mod e to the power z equals to mod e to the power x into e to the power iy equals to mod e to the power x, and e to the power iy equals to cos y plus I sin y. Then its modulus is nothing but e to the power x, and e to the power x is less than 1 for all x less than 0 where x belongs to R. Then mod of fz less than 1 for all z belongs to gamma, where gamma is z belongs to C such that x less than 0, which is not a bonded set, right? But gamma is unbonded. So what we get here, fz is entire and fz is mapping an unbonded set to a bonded set. That means fz is bonded on the unbonded set. Hence, it is not true that a non-constant entire function maps unbonded set to unbonded set. In this case, we got a bonded set for an unbonded set. Hence, option D is false. Then, this will be our answer. Now, question number 98. The number of zeros counting multiplicity of pz equals to 3 to the power 3 into z to the power 5 plus 2iz square plus 7iz plus 1 in the annular region z belongs to C such that 1 less than mod z less than 7 is. So this is nothing but the application of Rouche's theorem. So what is the theorem? The theorem is, suppose fz and gz are analytic inside and on a simple closed contour C with mod gz less than mod fz on C, then fz plus gz has the same number of zeros as fz inside C. So case 1, for mod z less than 1, pz is given. So we are breaking pz as fz equals to 2iz square plus 7iz and gz equals to 3z to the power 5 plus 1. Then mod of gz will be mod of 3z to the power 5 plus 1, which is less than equals to 3 mod to the power z5, mod z to the power 5 plus 1 equals to 4. On mod z equals to 1, it will be 4, right? Because on mod z equals to 1, mod of z to the power 5 equals to 1 and 3 plus 1 equals to 4, and mod of fz equals to mod 7iz plus 2iz square, which is greater than equals to 7iz minus 2iz square. Then it is equals to 7 minus 2, as on mod z equals to 1, z equals to 1, z square equals to 1. Therefore 7 minus 2 equals to 5. Therefore mod z is less than equals to 4 and mod fz is greater than equal to 5 on mod z equals to 1. That implies mod of gz less than mod of fz on mod z equals to 1. Now fz equals to, taking z common, z into 2iz plus 7i. Taking I common also equals to iz 2z plus 7. Then the zeros of fz are 0 and minus 7 by 2. but 0 lies inside mod z equals less than 1, and minus 7 by 2 equals to minus 3.5 is outside mod z less than 1. Therefore, fz has only one zero inside mod z less than 1, and that implies pz equals to fz plus gz by Rouche's theorem has one zero inside mod z less than 1. Now, case 2. For mod z less than 7. So, fz, we are taking fz equals to 3z to the power 5 and gz equals to 2iz square plus 7iz plus 1. Therefore, mod of fz will be 3 into on mod z equals to 1, z equals to 7, then 7 to the power 5, and mod of gz equals to mod of 2iz square plus 7iz plus 1, which is less than equals to 2iz square plus 7iz plus 1. On mod z equals to 7, we can put z equals to 7, then it is 2I mod of 7 square plus 7 into 7 mod 7 plus I. After simplification, we get equals to 148, and 148 is less than 3 into 7 to the power 5. Therefore, what we get, mod of gz is less than mod of fx on mod z equals to 7. Okay, I have written here mod of gz less than equals to 148 on mod z equals to 7, and mod of fz equals to 3 into 7 to the power 5. Hence, we can get that mod of gz less than equals to mod of fz, and fz was 3 into z to the power 5. Then z to the power 5 has 5 zeros inside mod z less than 7, as at z equals to 0, fz has zeros of multiplicity 5. Therefore, pz equals to fz plus gz has 5 zeros inside mod z equal less than 7. Therefore, pz has 4 zeros inside the annular region, because inside mod z less than 1 there was 1 0. Therefore, 5 minus 1 equals to 4. Hence, option D is true. So that's all.